problems involving vector operations. In this lesson, we're going to talk about how we add vectors in real life scenarios. So when you add two vectors, so like here's an example we're going to do with two tugboats. So we have tugboat 1 going this direction, tugboat 2 going that direction. The actual thing they're tugging is not going to go in either direction. It's going to go kind of a mixture of the two, depending on what force they're taking. In this case, right, if you add vector 2, which is going a little further, with vector 1, just move it to the top, which gets you this vector here, which we call the resultant vector. And that's the path that the ship's going to go on. And by the way, the force of each, you can tell by how much force by how long the vector is, or the magnitude of that vector. Same thing here. So this force 2 is a little longer than force 1, so it's a bigger force. And you can see the resultant force of the ship. So let's do an example that deals with all that. So example 1 is still water. Jocks can't swim at 1.5 meters per second. Remember, that's per second. That's why B does it. So same thing as saying meters over seconds. Jock is at point A on the edge of a canal. There he is. And considers point B to be direct opposites and all the way over there. A current is flowing from the left at a constant speed of 0.5 meters per second. So that is a current going that way. So you can try to swim from here to here, and the current's going that way. So A, if Jock dives in straight towards B and swims without allowing for current, which will actual speed be? So what they're generally saying is if you start swimming this way and the current affects you that way, like what's your actual speed going to be? It's not going to be 1.5 because the current's pushing you the direction. So how do we solve that? Well, first, let's just draw it real quick. So you start in A, and he's going in that direction with this single force. And he's going at 1.5 meters per second. The current's taking him to the right at a force of 0.5 meters per second. So Jock's actual path would be, it's like adding two vectors, it'd be this guy. That's Jock's actual path, right? So he's trying to swim this way, but the force is pushing him that way. So this is his actual path. And I want to find the speed. Speed, I'm not sure if I mentioned this, is magnitude in vectors. So speed is just the magnitude. That's all it is. So when we're talking about speed in vectors, we're talking about how long of a force we're drawing. So it's just the magnitude. And then we find the magnitude the way we always find it. This is a triangle. A little right angle right there. All right, so I'm just going to do a squared, b squared, c squared, because I just got to find the hypotenuse. That's all it is, just a triangle. So if I do a squared plus b squared equals c squared, I do some math. I'm going to do this in fractions. I should actually do it in fractions. Otherwise, I'm not going to know what the answers are. So I'm going to get 9 over 4 plus 1 over 4 equals c squared. So I get 10 over 4 equals c squared. Square root of that, I get rad 10 over 2. So equal to c. And that equals about 1.58 meters per second. So that's his actual speed, right? So he's going about 1.8 that way. So current's pushing this way, so he's actually going about 1.58 this way. Let's go to B. Jock wants to swim directly across the canal to point B. So he wants to swim over there. At what angle should Jock aim to swim in order that the current will correct his direction, right? So if you see right now, I started off here. I'm actually going this way because we're doing like that. I'm going this way, then going that way. So we're actually off kilter. He's going to hit somewhere over there. So we gotta adjust that angle. Well, that's just a trig problem, right? We have a triangle that has 1.5, 0.5, and we're going this way. I guess I could put that in. We're trying to figure out what this angle is, so we could overcorrect and put it on this side. So we could swim in that direction this way so that we get to where we want to go. And that's this trig. We have a right angle right here. We'll look at our sides. This is opposite. This will be hypotenuse. This will be adjacent. So I have the opposite side and the adjacent side. That's also known as TOA. So if I do tan theta of my angle, opposite or adjacent, I get like this. And I just have to put that on your calculator, so tan inverse both sides. And we probably want this in degrees. Luckily I did this work already. So there we go. So tan inverse 0.5 over 1.5, I get about 18.43 degrees. So it's about 18.4 degrees. Is the angle we should overcorrect to. So we should actually swim like this way at 18 degrees. That way when I'm running that way, the current pushed me back in the correct path. So that's the idea there. Now let's see the second part of B. What is Jock's actual speed? So what's this talking about? What's going on here is this. Now that we're correcting our path, right? So here is B and here is A. We're not going straight anymore. Now we know, like, we have to go to this angle. So we're going to go at an angle of 18.4. like this is a straight line. And then I'm still swimming at my rate of 1.5 from earlier. And then the current's gonna take me this way to correct my distance at 0.5. What's my actual speed right here? So what is this? What's my new vector since I'm going straight? How's this different than before? Well, look at our triangle before. I was going straight and the current was taking me to the side. So the thing I was looking for was my hypotenuse. This time, my hypotenuse is the current I'm running, and then we're looking for one of the legs. So we're gonna do this just like before: a squared, b squared, c squared. So I'm gonna get 1/2 squared plus b squared equals 3/2 squared. I might just put in my calculator if I wanted to, but let's just do this real quick. That is 9/4. Subtract b squared equals minus 1/4 minus 1/4 8/4 square root, and I get b squared equals rad 8 over 2, or 2 rad 2 over 2, which is just rad 2. In a calculator, rad 2 is like 1 point something, 1.57 I think. Square root of 2, 1.41. So embarrassed. Well, not degrees, sorry. So that's my actual speed. It's going about 1.41 straight ahead, since he has to overcorrect with the speed. That's the video.